Okay, so last time we kind of finished up chapter 7, I think, and talked about different types of reactions. So we're off to chapter 9, and here we're going to talk about putting together a couple of things from the previous chapters, balancing equations, and sort of grams, moles, and figuring out again how much we should produce in a reaction. We're going to talk about stoichiometry and some different parts of stoichiometry in this chapter. Again, a reminder that one of the main conversions that we do use in this chapter for sure is that conversion between grams to moles and moles to grams. And that is the molar mass that we do use as a conversion factor from it. And again, a reminder that we do get the molar mass from the periodic table. So again, if you had something like hydrogen, or maybe oxygen as well. It is these numbers on the bottom, which is how many grams there are per mole. So if we had something again like water, we would go 2 times 1.008 grams per mole. And that is the molar mass from the periodic table of the two hydrogens, plus our 16 grams per mole, which is our molar mass of our oxygen. And that gives us 18.02 grams per mole as the molar mass of water. Molar mass really is a conversion factor. You could use it in dimensional analysis. You could use it like it is here, grams per mole. Or if you needed to, you can flip it around, moles per grams. And again, if we had something like 43.5 grams of water and we want to know how many moles of it, we would just set it up dimensional analysis way here using our conversion factor from the periodic table to do so. Again, 18.02 grams per mole of water. Grams will cancel. And in this case, get just something like 43.5 divided by 18.02, something like 2.41 moles of water. We also very commonly do this as really our first step in kind of the stoichiometry problems we're going to do. We also on the back end oftentimes will be going kind of the back way here and need to go from say moles back to grams. That again is also the molar mass. So, if we had something like C2H4, we would get the molar mass from the periodic table. Again, carbon would be 12.01, and we would add it up there 2 times 12.01 grams per mole, which is our carbons, plus 4 times 1.008 grams per mole, which is our hydrogens. And it is typical when you do take the molar mass off the periodic table, or just in general when you calculate molar mass, that usually 4 significant figures is pretty much what you take the molar mass to. That would get us something like 28.05 grams per mole as our molar mass for C2H4. Once again, we could use that as a conversion factor, and that would be, if we had, say, 0.5 moles of C2H4 and we wanted grams, we'd do the same thing. Opposites cancel. We would need the moles on the bottom, 28.05 grams up on top, and we would get zero point 0.5 times 28.05, giving us something like 14.0 grams there of C2H4. So in these stoichiometry problems, these are two very common conversions that we use a lot. A reminder, this is chapter 8 stuff, I think, is where we did this. And if you're not, you can reference chapter 8 one more time. But definitely kind of at the beginning, we oftentimes do this conversion, grams to moles. And on the back end, a lot of times with the calculation, we go moles back to grams using it. Now, a very common mistake that people make, especially when they're doing sort of stoichiometry problems like we will do in this chapter, is they will want to do the molar mass sort of incorrectly. And what I mean by that is what will happen is they will look at, say, an equation And when they look at the equation that's balanced, let's just say, for example, on one side of the arrow, you had 6 waters or something. And when they go to use the molar mass, they want to incorporate the coefficient, and you should never do that. Molar mass is basically just based off the formula by itself. So you just add up all the parts of one of the formulas. That is basically what the definition of molar mass is, how many grams there are per 1 mole, which means it is just there. So again, we would use the 18.02 here for the water. We would not incorporate the 6 in the molar mass part of the calculation. And as we'll talk about, where we will incorporate that in a different part of the calculation. It's actually the stoichiometry part, but you don't want to do that twice. And it's a very, very common error that people make, which is they want to kind of incorporate it in the molar mass. So molar mass should always be just the formula by itself. Doesn't matter what the coefficient may be in the balanced equation. If it is an equation, just what one of those formulas are, add up all the parts from the periodic table, bottom number basically, and again, about 4 significant figures. Any questions on that there? Okay. So let's talk about really ways we could look at a chemical equation or reaction. We could look at the coefficients as the molecules, for example. That's 2 molecules of H2 react with 1 molecule of O2 to give you 2 molecules of H2O. Really, the relationship that we use for stoichiometry and really in this chapter is this mole to mole relationship. And we also get that just solely from the actual coefficient in the balanced equation. 2 moles of hydrogen, 1 mole of oxygen, 2 moles of H2O. The last part we really don't use too much in these calculations, but this is the conservation of mass. Since we have a balanced equation, we got the same number of elements on each side of the arrow. Again, the hydrogen on the left is 1.008 grams. The hydrogen on the right is 1.008 grams. So we should have the same mass of each element on each side. And that gives us, again, 36 grams of reactants, should give us about 36 grams of products. So what we're going to look at is stoichiometry, which is really a fancy way of just saying a conversion factor, basically. And in stoichiometry type calculations, one of the reasons we need to do it is oftentimes we're given an equation and we're given some information about somebody in the equation, but we're not actually interested in that thing. We're interested in somebody else in the equation. So we need a way to convert from whatever information they gave us to what we're actually looking for. May that be how much products you would produce, how much reactants you would start with. And the big deal about stoichiometry is it's actually just a conversion factor that you get from the balanced equation. So instead of sort of looking it up in a book or a table, you actually look at the actual equation and you use that as a conversion factor. And things that we want to know is, like I said, if you pretty much know one piece of information about anybody in a chemical reaction, you could do some stoichiometry type calculations and you can figure out all kinds of things. Like it says there, again, if you started with a certain amount of reactants, you can figure out how much products you should have produced. If you know how much products you produce, you could back calculate and figure out how much reactants you started with. And sometimes, though, as we'll talk about, people think you have to do stoichiometry always sort of crossing over the arrow from one side to the next, and you don't. You can stay, for example, on the reactant side and figure out, between these two reactants, how much of one you need to react with the other. You could also stay on the product side and do sort of the relationship between the two products. And if you know how much of one product you produce, you could also figure out how much of the other product you would produce as well. So sometimes people think you always have to kind of cross the arrow when you're doing these type of calculations, and you don't. You could do it really for anybody on any side of the arrow that you want. The units that we'll deal with, and we'll see stoichiometry pop up in different places, but in this chapter, probably grams and moles are very common sort of units. Liters, oftentimes, we see in gases and molarity and stuff like that. Molarity and volume, we see like when we talk about solutions. So the mole method here is the method we use for stoichiometry, and it's based on the idea that the coefficient in the balance equation represents the moles of each of those things, and then we could have sort of a relationship for it. There's several steps to follow in a basic stoichiometry problem, and a lot of times I would say that perhaps the first one's kind of done for you. But just in case it's not, a reminder that if you have everybody in words and they're telling you in words how the reaction is happening, you want to make sure that you first start off with the correct formulas, just like you're doing naming. Once you have the correct formulas in the equation, that's your unbalanced equation. Pretty much nothing works right if you do not have a balanced equation. So that should always be your first step, really, is to make sure you do have a balanced equation. You want to take whatever they give you, basically, and get it to grams. And then from grams, you want to get it to moles. And again, that is the molar mass conversion we were just talking about from the periodic table. That's going to allow you to do that. Once you have that, then it's time for the big mole to mole relationship, and that's from your balanced equation. And that's the stoichiometry part. That's going to take you from what you're not interested in to what you are interested in. And lastly, very commonly, back end of the calculation, moles to some other units, and a lot of times molar mass will kind of pop its head back over to here. So really in basic stoichiometry problems, you can basically break it down to 4 steps. You want to make sure you have a balanced equation. You want to get whatever it is to grams and then grams to moles. You want to do the stoichiometry part, which is the mole to mole relationship. And that is from the equation. And then, if necessary, take those moles to some other unit. So for basic stoichiometry problems, pretty much you follow those 4 steps in that order, by the way. And if something is done for you, then you just go forward. Don't ever go backwards, yes, and undo things. Just kind of go forward along the way. So how do we get these relationships? Well, if we look at an equation that's balanced like this one here, from this one single equation, we could have a bunch of different stoichiometric equivalents or equalities that we could get from it. And again, here, we're just looking at the coefficients. So from this equation, we could say there are 2 moles of CO2, CO, gives us 1 mole there of O2. We could also say that for every 2 moles of CO we put in there, we get 2 moles of CO2 out. And for every 1 mole of O2, we get 2 moles of CO2 out. These are what are referred to as stoichiometric equivalents or qualities. They are not equal to each other. Obviously, 2 does not equal 1, but they are equal to each other in terms of proportion of each of those that you need for this reaction to actually take place. Now, since those are technically equalities, like any equality we talked about, like in chapter 2, you could write 2 conversion factors for it. You could write 2 moles of CO over 1 mole of O2, or 1 mole of O2 over 2 moles of CO. For this one, you could write 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. And lastly, here we could write 1 mole of O2 over 2 moles of CO2. I'll get that right. Our 2 moles of CO2 gives us 1 mole of O2. So we have basically 3 equalities that we could get from this equation. We also have 6 conversion factors that we could actually use. Will you use all 6 of them? I hope not, because you're probably doing something wrong if you are. You actually will probably just use 1 in most cases. So whatever ones you're interested in, you would pick. Any questions on how we get that? And again, this is the big stoichiometry move here, which is really just a conversion factor that you get from the equation. And again, you're just going to kind of do dimensional analysis and pick the one that's going to cancel it out. So for example, just say if we went through like kind of a little quick problem here with this one. Let's say that we produced 32 grams of CO2, and we want to know how many grams of O2 did we kind of start with. So what we would want to do is kind of run through our calculation here. So our 4 steps. So first step is we need a balanced equation, which obviously step number 1 here is done. The second step that we need to do is take whatever they gave us, go from grams to moles, which we do need to do in this case. So we will need the molar mass of CO2 to do that. So we would need to go to the periodic table there, and we would find carbon, that's 12.01. We would find oxygen, which is 16. And we would get the molar mass of CO2 by taking 12.01 for the carbon, add it to 2 times 16 for oxygen. That's going to give us 4401 grams per mole. So again, we're going to use that as a conversion factor here to do our second step, which is I'm going to take the 32 grams of CO2. I'm going to set it up here. Opposites cancel. So in this case, grams do need to go on the bottom, and that will give me moles of CO2 here. The grams would cancel. You don't necessarily have to get a number at this point, but if you did, just so we can see all the individual steps here, you would end up with something like 0.72711. I'm not going to round just yet. I'm going to kind of keep a couple of digits. First off, any questions on that part of the calculation? Now, if we look at our equation, the third step that we want to do is really the stoichiometry step. So this is the mole to mole relationship. So what 2 things should you be interested in? Well, in this case, I'm interested in the CO2 because that is what was given to me. And clearly I'm looking for O2, so that is the other thing I'm interested in. We did this a second ago. That's going to give us this equality. And that's going to give us an option of this conversion factor and this conversion factor to use. So because we're setting it up in dimensional analysis, we should know that opposites cancel, which means in this case, I actually want the CO2 to be on the bottom. So I would use the conversion factor from the equation that has the CO2 on the bottom, and that would give me 1 mole of O2 and 2 moles of CO2. And if you blink your eyes there really quickly, that is the big stoichiometry move pretty much right there. Again, it's really just a conversion factor that you get from the equation. This again is going to cancel here. And now we have successfully converted out of CO2. And now in terms of units, we are in moles of O2, which would be 0.363. Again, I'm not going to round too much right at this point. Any questions up to there? Now, in this case, if I wanted moles, I would be done. I basically could put a box around it, but I don't want moles, right? I do want grams in this case, so I do need to do the 4th step, which is to take my moles, in this case, back to grams. And it could be any unit, by the way. It could be asked for like pounds or something like that, or kilograms or something like that. But here, we just want grams. That again is the molar mass conversion that I need to do that. But we need to remember that we are no longer at CO2. I do have to go back to the periodic table and get the molar mass for O2 because that's currently where we're at in terms of our units. So once again, I would go back to the periodic table, calculate my molar mass there for O2. Again, we don't want to use CO2s at this point. That's 32 grams per mole. And to finish out my calculation here, I'll take my number, moles of O2. In this case, moles are on top, so I do want moles of O2 on the bottom and 32 grams of O2 up on top. Moles are going to cancel, and there we go. That's going to give us 11 point, we'll call it 6 grams of O2. And that would be my 4th step. So really all basic stoichiometry problems are these 4 steps. Any questions on those 4 steps? So basically what this number represents is if I did produce 32 grams of CO2, I would have had to put in there about 11.6 grams of O2 to actually produce that much product in this case. Now I did it kind of step by step here and got an answer in between. You don't have to do that. In fact, here they kind of encourage you not to, but I don't really care if you want to get an answer in between. You go from here to here to here to here. You can do it all in one calculation. Is perfectly fine without getting the answers in between. If you do get the answers in between, like I said, I'm okay with it. But again, I would not round too much until the very end so you don't get any type of rounding error and stuff like that. Any questions on that 4 steps there? All right, let's try some then, maybe. And that's what we just talked about. So I'll just scroll through it here. Let's try this one here. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. In this case, we want to know how many moles of hydrogen can be formed by the reaction of 5.32 moles of lithium with water. So why don't you give it a go? Again, follow those 4 sort of steps. Once again, you need a balanced equation, which I don't see, so I would probably start there. You need to convert to moles. You need to do the stoichiometry mole to mole. Okay, so let's take a look, see how you're doing. So again, starting with step number 1, we need a balanced equation, and we do have everything in words. So we just want to make sure we get all the proper formulas down first. So lithium metal would be just Li, reacts with water, which I hope is H2O, giving us hydrogen gas. Remember, hydrogen gas is diatomic, so that should be H2, and a little lithium hydroxide, LiOH. Again, I don't really care about the balancing part until I get the proper formulas down, which I do have here, and then I do need to balance it here, perhaps. And let's see here. We got lithium. We got 2 of those, just 1 of those. So maybe like I don't know, like a 2, and a 2. I feel like I'm just putting 2. So let's see, 2 lithiums, 4 hydrogens, and 2 oxygens. 2 oxygens looks like a winner, I think, in that case. Any questions on that so far? So remember, formulas first, then balance. Don't try to do them together. Next, really the only piece of information given to us in this problem is we have 5.32 moles of lithium, and we're ultimately looking for how many moles of hydrogen in this case. So step number 1 is done. Step number 2 is again already done for you, so don't unconvert it. So I don't need to do that. That means I'm off to step number 3 already, which is I want to do my mole to mole relationship. So clearly I'm interested in lithium because that's what's given to me. And I am interested in hydrogen because that is what I'm looking for. Once again, we're going to find the mole to mole relationship. That is 2 moles of lithium gives me 1 mole of H2. And again, that just comes from the coefficients. That again does give me an option of 2 conversion factors, 2 moles of lithium, 1 mole of H2, or 1 mole of H2 over 2 moles of lithium. So starting with my number here, 5.32 moles of lithium. Opposites cancel, so I will need moles of lithium on the bottom, which means I do want to use the conversion factor on the right. 1 mole of hydrogen gives me 2 moles of lithium. The moles of lithium are going to cancel, and that's going to get me 5.32 divided by 2, a 2.66 moles of hydrogen, which means I am done with that step right there. In this particular case, I'm actually done, as that is what I'm looking for. I'm looking for moles. I'm not looking for grams, so I don't have to do the 4th step. By the way, that would be known as the theoretical yield in moles, basically, of hydrogen, which is the maximum amount of product that you should make. By the way, just out of curiosity, if I did want grams, what I would need is the molar mass, right, of H2 here from the periodic table. I would have to do something like 2.1008 grams per mole of H2 grams per H2 per mole of H2. And that would get me, not that it asks for, 2.016, about 5.36 grams of H2 would be my theoretical yield in this case of in grams. Yeah. Any question on any of those steps there? All right, let's try another one here using the same reaction, I think. All right, so for this one, we do want to know how many grams of H2 would be formed if we started with 81.75 grams of lithium. Lithium is 6.941 on the periodic table. Obviously here, hydrogen is 1.008. Okay, so let's take a look. So again, we're going to follow the steps here. So obviously our equation is balanced from last time, so we're good. In this case, we're given 81.75 grams of lithium. In this case, we're looking for grams of H2. So we do need to do step number 2, which is convert to moles. We will again need the molar mass from the periodic table of H2. So that is 2 times 1.008 grams per mole. That's going to give us a molar mass, or really a conversion factor here of 2.016 grams per mole. We're going to start with taking what was given to us, which is 81.75 grams of lithium. Again, that is definitely not the right molar mass there, huh? We actually are starting with lithium, so we'll use that guy right there, which is 6.941 grams per mole. That was much calculated. So we'll use our molar mass here of lithium, which is 6.941 grams per mole of lithium. Once again, you don't really need to get an answer, but I am going to do it just so you can see again all the steps. So we'll get something like 11.7778. Again, I'm not going to round too much at this point. That takes care of converting to moles. And really the reason you do need to convert it to moles is for the stoichiometry part, and that is the mole-to-mole relationship, which is the third step. And once again, since we're doing the same two guys, that's going to give us our same relationship here for our third step, which is again 2 moles of lithium from the balanced equation gives us 1 mole of H2. That again is going to give us our 2 conversion factor options. Once again, you don't necessarily have to write the conversion factors, but again, just to see our 2 options here. So continuing on here with our number, 11.7778 moles of lithium. This is going to give us our big stoichiometry move where, again, we want to get rid of lithium, so it's going to go on the bottom. And 1 mole of H2 up on top. And at this point, if we got an answer, we'd be looking at 5.8889 moles of H2. So that would be the third step. Here we will need to do the fourth step because we are looking for grams in this case. So we will need the molar mass of H2. So I guess I just jumped the gun on that one. That is the molar mass there of H2 from the periodic table to do our fourth step. And again, opposites cancel, so we will need moles on the bottom of H2 is 2.016 grams of H2. And that will get us, looks like 11.87 grams of H2. That would be, again, our theoretical yield in grams. And by the way, that would be our theoretical yield in moles. Any questions on that? Again, same 4 steps along the way. And once again, you can go from calculation to calculation to calculation, basically. Yeah. Any questions on any of that? Any questions? No. All right, let's try another one here. Make sure. Hopefully they get the same answer. Go. All right, try this one here. If we took 765 grams of C6H12O6, how many grams of CO2 would we produce? So we're looking for grams of CO2, and we're starting with 765 grams of this guy. So carbon 12.01, hydrogen 1.008, oxygen 16 here. Okay, let's take a look since we're getting to the end here. We're going to follow again our 4 steps, always in a basic stoichiometry problem. I would say that if you probably see coefficients, it's probably balanced, but it's a good idea to check it, but it is in this case, so we are good. Second step is take what they gave us, which is this guy, and convert it into moles. We do need to do that. In order to do that, again, we do need the molar mass of that guy there from the periodic table. So C6H12O6, just going to add up all the parts. There are 6 carbons at 12.01. There are 12 hydrogens at 1.008 from the periodic table. There are 6 oxygens at 16 from the periodic table. Going to give us 180.2 grams per mole as our molar mass. Again, that's going to be our conversion factor here. So we'll start with what was given to us, 765. We'll use our molar mass as our conversion factor. Again, we want grams to cancel, so we do need to put the grams on the bottom, the moles up on top. The grams are going to cancel, and again, if you got a number at this point, 765 divided by 180.2, going to get you something like 4.2453. Again, I'm not going to round too much at this point. Moles of C6H12O6. At this point, we are now ready to do our third step, which is really the stoichiometry step. We'll go to our equation, and obviously that is what we're interested in. And in this case, we're interested in the CO2 as well. And we can find a relationship from the balance equation coefficients. That means for every 1 mole of C6H12O6 I throw in there, I'm going to get out 6 moles of CO2. Once again, that does give us 2 conversion factor options to use. Looks like this, or we just flip it, and looks like this as our other option. So taking our number from the previous step there, 4.2 looks like 453 moles of C6H12O6. We want to get rid of that, so we're going to use conversion factor here on the right to do so. That will get us 6 moles of CO2 up on top, 1 mole of our C6H12O6 that we want to get rid of on the bottom, and that will yield us there about 25.4717 moles of CO2. Once again, if we were interested in just moles, we would be done at this point. That is also our theoretical yield in moles, but we do want grams, so we do have to do the 4th step. That is going to require us to get the molar mass of CO2 at this point. Going back to the periodic table, 12.01 for the 1 carbon, plus 2 times our 16 for our oxygens there, giving us 4401 grams per mole. Taking our number from above, 25.4717 moles of CO2. Once again, using our molar mass as our conversion factor here on the back end. Grams on top, moles on the bottom, so they cancel. Going to get us here, looks like about 1,121 grams of CO2. And since we only started with 3 sig figs, maybe about 1120 grams of CO2 might be good, as that was the only number here, which was 3 significant figures in this calculation. Once again, hopefully, again, you can see the patterns. Step 1, balance equation, convert to moles, stoichiometry, mole to mole relationship from the equation, and convert those guys. Once again, you can do it all in one calculation or break it up along the way. Any questions on that there?